Okay, welcome back. We're moving on to chapter 11, which is closed form solutions to nonlinear ODEs. And in particular, these are going to be stuck with first order one-dimensional because that's like the extent that we can actually solve these in closed form in somewhat of a general sense. So that's pretty restrictive, right? Because these first order linear problems in one dimension, we could solve all of them really easily. But in nonlinear problems, it's a subset. It's a considerable subset of the nonlinear ODEs, even in first order one dimension, that we have the ability to solve. And I start out with this theorem that's kind of in section 0 of chapter 11 because it's the overarching theorem that's going to motivate us throughout the entire chapter. It's basically the way that we do know how to solve nonlinear ODEs in some sort of a closed form. And the way it works, the way this theorem works, is that you start with a nonlinear ODE, first order, right? There's only one derivative there. It's in one dimension. It's y is a function of r, and x is just sitting in r, and the image of y is in r as well. So we're nonlinear in one dimension. Basically, g is now a function of two variables. It's a function of x and y. And if, right, there's an if right here. So if we can write g as the negative partial derivative in x divided by partial derivative in y of some two-dimensional function. So maybe I'll make this clear right here. So if we can write the right-hand side, as in that, as a ratio of partial derivatives of a function f. So if you write it as a ratio of partial derivatives of a function f, then the implicit solution to the ODE is given by f of xy equals c for any c in r. This for any c in r, this is the free parameter we can use to fit initial conditions. Okay, so however, this solution is implicit, right? Right here, that's not solved for y. It's not saying y of x equals some function of x, which depends on c as well. It's implicit in its current form. We could possibly invert it to solve for y, and then we would have something explicit. So, if we can solve for y, which would be y of x in that case, then we can make it explicit. We can make the solution explicit, but that's just not necessarily going to be possible. Okay, so but this is the overarching theorem. It just says, hey, if we can interpret g as a ratio of a partial derivative in x divided by a partial derivative in y, then whatever that function was, which we were able to take partial derivatives of and take a ratio and get g, if you set that function equal to a constant, you get an implicit solution. The rest of this chapter is basically saying, hey, how can I actually do this? Because it turns out it's not this procedure right here, figuring out what function exists so that when you take a ratio and you set it equal to g, you get something meaningful, is not an easy thing to do. And so that's what the whole chapter is kind of stuck around. So we'll start right here in section 11.1, which is called the total differential in smooth level sets. And we're just going to recall this definition that you probably saw in Calculus 3 of the total differential of a function. It gets notated by df, little d, on a function f. And on the right-hand side, we have a bunch of differentials, dxj. Okay, so think about this here. That's really saying f is a function of x1, x2, x3. You can take some dots, xd, right? And because of that, you can take d different partial derivatives of f. And those d different partial derivatives are kind of squished together into this sum where we represent differentials in each of the variables we computed the partial derivative of independently. The way this actually works, you can make this much more rigorous. These are elements of a tangent space. If you're curious about that terminology, look for our course in differential geometry. Which is spanned by the basis dx1, dx2, dx sub d. So you have these bases of differentials which span a tangent space, and the total differential is an element of that. So you can kind of see it looks like a linear combination of partial derivatives of f against like the basis, which is dx1, dx2, and so on. So that's how that should look familiar to you a little bit. Or you can interpret it in the meaning of Calculus 3, where it was just defined and you just accepted it for what it was. And we can compute an example of this. I won't go through this example, but I would urge you to maybe just, if you feel a little bit uncertain about your partial derivatives, just take some partial derivatives of this function and make sure that you're getting what you should get for the x and y partial derivative there. Okay, so let's look at the next definition that we have is the level set or level curve or level surface, depending on the dimension we sit in. This is just the preimage of the singleton C of some constant, right? So you have a constant in R, you take the preimage of that constant, and that's your level set or your level curve. And so it just gets defined the same way that we would always define our preimages. I use the notation LS sub C of my function, so it's the level set with respect to C of that function. But I mean, the notation is just as good to say it's the preimage of the singleton. And then we have this extra definition for level curve when D is 2, or level surface when D is greater than or equal to 3. Sometimes you'll see hypersurface here instead of just surface. And that's going to occur if you can take a gradient of f and it's non-zero on the level curve. Okay, so if I take a gradient and it's non-zero on a level curve, then I have a level surface or level curve. So let's look at an example of that. A very classic example would be like the paraboloid. This is jumping back to Calc 3 for a lot of you. So we have like this function, which looks like the following. Let's say paraboloid. And it kind of has its nice parabolic shape to it. The level surface of a positive number, r squared, is going to be the intersection of a plane with the paraboloid. And where a plane intersects a paraboloid is a circle. And in fact, that's a level curve because we're in 2 dimensions, right? There's 2 inputs to f. So we're in 2 dimensions, and you'll find that the gradient of f is perfectly well defined. It's 2x comma 2y, and it's only 0 when x and y are 0. So you definitely have a level curve. The circle is a level curve. Okay, if I scroll down a little bit more, we see that the next theorem basically is a way of me proving the theorem that I began this lecture with. So you can read through that theorem if you want. It's basically, like I said, it's the proof. It says, hey, this thing that I was claiming was the implicit solution is a level curve, right? You should be able to recognize that as a level curve now. You compute the total differential on the level curve, and you get that the total differential is 0 because the function's constant on the level curve. You then rearrange the total differential, which you now know is equal to 0, and you recover exactly the derivative of y is negative partial x divided by partial y. So that's really that theorem there is a proof of the first theorem. And then let's look at an example, right? So jumping back to the paraboloid, let's maybe compute the ratio of the partial derivative in x divided by the partial derivative in y. Let's verify that this is true. This is the negative partial f partial x divided by partial f partial y, which is negative 2x divided by 2y. And of course the 2's cancel. And yes, we have negative x over y. Okay, fine. So what our original theorem said is if we have this function, which produces g, or in this case negative x over y, then the solution must be given by f of x, y equals c, the level curve. Well, f of x, y is x squared plus y squared. So the solution is given by x squared plus y squared equals c. And if we want to solve for y, then we do that, and we get y is y squared is c minus x squared, or rather that y is plus or minus root c minus x squared. And so we have a solution. It turns out the solution to that differential equation is plus or minus root c minus x squared. And that's really kind of the whole point of this section. But so far what we've been doing in section 11.1 is moving in the forwards direction. We're saying, hey, if we're given a function and we construct a differential equation, then the solution to that differential equation must be given by the function equal to a constant. Working in reverse is a lot trickier, and we're going to take one in-between step in the next section to then get to section 11.3, which is the really important one for working backwards. But for now, we're going to move on to 11.2, which says closed exact forms and existence of a primitive function. So closed and exact forms are special cases of total differentials. So these are special cases. Actually, they're special cases of differential forms which may or may not, be total, right? They might be total differentials, they might not be total differentials, and actually closed and exact are one way of us testing whether or not these are total differentials. Okay, so we're going to define a closed form as just a collection of functions in front of my x and y differentials, some function of x and y, another function of x and y, that are in front of differentials at dx and dy, with the specific property that if I compute a partial derivative of m in y and a partial derivative of n in x, that they're equal to one another. We're going to call those closed. And I think this was something you probably encountered in Calc 3 as well. And I have an example of a differential form which happens to be closed here, because if we computed a derivative in y, we get the following. If we compute a derivative in x, we get the same. And so since the x derivative of n and the y derivative of m were equal, then we have something that's closed. Now, what's nice is that we're going to see that these closed forms have what we call a primitive function. But let's actually define what a primitive function might be. In a primitive function, you start with a differential form, which is just some collection of functions. It's an element of the tangent space, right? It's a collection of functions or function coefficients on this basis, and we just give it a name, omega. It's just a common name for a differential form. But just think about this as an element of a vector space with a very particular basis, dxj. And if, right, so the element of this space won't necessarily be a total differential, but if there exists a function for which it is a total differential, maybe I'll make this clearer. What this is saying is if omega is actually the total differential of some function f, then we call f a primitive of omega. Right, so f is called the primitive function for or of omega. So a primitive in the sense that under the differential, you recover omega. So in some sense, we're thinking along the lines of antiderivatives, right? If omega is a differential, then its primitive is like an antiderivative. That's how we can think about it. So let's look at the following example. I say this function x cubed y squared plus 3x squared y cubed is a primitive for the differential form. And I give the following differential form right here. And we can find out that it is a primitive of that because we can compute the partials in x and in y and actually recover that differential form, right? But theoretically, you would say, so suppose that existed in the first place, give this the name omega, right? If you give this entire piece the name omega, then do we necessarily know that omega is a differential form? We don't know that until we find a primitive, if that makes sense. So we don't know omega is a differential form or a total differential until we find a primitive. But in this case, we were given the primitive, which is useful, right? We just verified that was a primitive for the differential form. Now we also have something called an exact form, and an exact form is exactly these forms which do have a primitive. So it's saying what's the difference between an exact form and a total differential? Nothing. Okay. But they're different names because in one case, the total differential basically says, hey, start with f, end up with a differential form. The exact form says, hey, I'm going to start with a form. Can I extract an f? Can I extract a primitive? So it's, we're talking about two different directions of kind of the same objects. So these exact forms are differential forms which have primitives. And that's to say that, there's some function f for which the derivative in x is m and the derivative in y is n. And so we can just do the reverse of my previous example and recover that, yes, that differential form is exact since there exists a primitive. Okay, the next theorem is the entire theorem of section 11.2, and that's that closed equals exact in 2 dimensions. Okay, so if I take a 2-dimensional differential form and it's closed, recall closed means that, okay, so let's say the 2-dimensional differential form, let's take w is m dx plus n dy. Closed, so some blue here, closed means partial m partial y equals partial n partial x. This theorem says that that's the same as exact, which means omega equals total differential of f. So those are two different definitions which happen to be equivalent in 2 dimensions. So that's something that's really profound because these definitions are not the same and yet they mean the same thing in 2 dimensions. The proof's going to be an exercise. It's not that difficult. Think about how the second derivatives in x and y, if you take a derivative in x and y of f, how do they interact? But that's going to be an exercise. But that's something that's really nice to know, is that you can test for the existence of a primitive by computing closedness. So that's what I'm saying in the next example. Rather than proving that that differential form is exact by finding a primitive, we know it's exact since we've proven it's closed, which was back at the beginning of this section. The next lemma is very efficient. I call it the anti-gradient. And that basically says, hey, if I'm given a gradient of a scalar field, something like gradient of f, you can actually recover the original f by the following computation. You take f at the 0, so you might not know this number, so this could be your constant of integration, and then you integrate from 0 to 1 of x dot the gradient of f of tx dt. Okay, so that's going to always reproduce the original scalar function from a gradient. And then the theorem, that was a lemma because it leads us to this theorem where what we can do is if we start with an exact form, which thanks to the previous theorem is a closed form. So if we start with either an exact or a closed form, we can actually recover the primitive. And it's a primitive because it's unique up to a constant, but we can recover a primitive by taking x and then integrating from 0 to 1 m of tx comma ty, and then adding y, the integral 0 to 1 n of tx ty dt. So we just put t's inside of m and n, multiply n by x, n by y, and add them together, and we can actually recover a primitive. And that's a very useful theorem for where we're headed here. I've got a nice footnote about a generalized version of my anti-gradient, which is known as the generalized Stokes theorem. Once again, that's a result of differential geometry. But the proof of my theorem there will be an exercise for you. It's not that bad. It's similar to the proof of the lemma where you have the fundamental theorem of line integrals. That's another Calculus 3 topic for you. And then we have one more example. We've been using the exact same function. I don't know if you've realized this. Every example in this section is the same, either primitive function or differential form, but we're just arriving at the results in different manners. So finally, we have something like this, which we know is closed and hence exact because we can calculate that. We find a primitive just by calculating x, the integral of m, on tx and ty. So every x and y we replace with a t. Same with y on n. Go through that integration, we end up with x cubed y squared plus 3x squared y cubed, which is in fact the primitive we were starting with this whole time. So that's what we have. That's the first two sections of chapter 11, and that's all I have for today. I'll see you in class. Bye.